talk about an application, in a sense, of some of the ideas that that Justin presented in his talk regarding 3D TQFTs, 3D A and B models, and that have come up in several of the other talks at this workshop. And it's an application to Humphrey homology. So this is based on work with Justin and my former student Nick Garner, Alexei Blomkov, and Lev Rozansky. So a lot of this conference has also been about like algebraic versus analytic approaches to moduli spaces of gauged maps and vortices, and the Humphrey homology application is one place where there are some simple things that can be done algebraically for what are called algebraic links. But if one wants an analogous computation for an arbitrary link, it's not algebraic, one is really forced into an analytic setting. And so I'll try by the end of the talk to actually state an analytic problem. I want to call it a conjecture, but I can't yet properly define the moduli space that needs to appear there. And I'll do that after describing what we do understand on the algebraic side. I should also say, so there's vortices appear in the A side of this story. As Justin said in his first talk, it's a little boring to just talk about the A side if one doesn't talk about the B side. What I'll discuss is 3D mirror to a B model, to a 3D B model construction. Of Blomkov and Rozansky. And so this construction is one path to Humphrey homology in terms of sheaves on Hilbert schemes on C2. I'll try to explain a little in physics terms of where that comes from. Both the A and B perspectives in the physics world ultimately descend from the now classic work of Gukov, Schwartz, and Waffe proposing both doubly and triply graded homology theories, both Kovanev and Humphrey homology, proposing that should come from counting BPS states in M theory on conifolds with certain branes. Some theory construction. And so I'm not going to talk about that at all. But just to say that the 3D field theories that appear here are actually describing certain M2 branes whose BPS states are supposed to give knot homology in this setup. So I will talk about Humphrey homology because that's the thing that was related to these theories that I love and have been studying for a few years now with Justin and others, to 3D n equals 4 theories and their twists. So Humphrey is called a triply graded homology theory for reasons I'll describe in a second. If one just wants doubly graded theories, Kovanov homology, then one doesn't need 3D TQFT, it's enough to use 2D TQFT. So the story is all closely related to many constructions in 2D. A models and B models. And in particular, I have in mind Seidel-Smith and Kautis-Kamnitzer on the two sides, and recent work of Mina Aganadich. Humphrey is where one needs to sort of couple a 2D A and B model to a three-dimensional bulk and actually use the power of 3D TQFT and techniques that are being developed there. Let me just to get us on the same page, review some things about the Humphrey polynomial. So what are we aiming for? Given a link, which the Humphrey polynomial is an invariant of links in S3. So one constructs a polynomial in, I'm going to use some funny conventions. So it's a polynomial in variables in my conventions a to plus minus a half, it's a Laurent polynomial, and q to the half minus q to the minus a half to the plus minus a half. It's a Laurent polynomial in a to the half and q to the half minus q to the minus a half. This thing is usually called the u, well, it has different names. It's often called the u variable. And one way, a very elementary way to construct this is from a skein relation combinatorially. So it's the skein relation that looks like this. Together with P of the unknot. So there are different normalizations here, and the one that's going to be relevant for an example I may get to at the end of the talk is a to the half minus a half over q to the half minus q to the minus a half. And the specialization, so this, the Jones polynomial, or rather, the quantum invariant for SLN with the fundamental representation, generalizing Jones to SLN is obtained by setting A to be Q to the N. Right, so the degree that's going to show up in homology will two degrees that will correspond to powers of A and powers of Q. And then one needs to understand what it means for something that's not a polynomial in Q to be categorified by a homology theory that's graded by Q degree. And so the other thing I should say for called the unreduced homology will expand around Q equals 0 in a Laurent series in Q. Something of the form A over Q to some power times write it like this. So one can expand to get the Humphrey to look like A over Q to some power times an element in Laurent series. In Q and polynomials. That's just rewriting, not super interesting. And so the example for the unknot, the thing that gets categorified, looks like maybe Q to the minus a half. 1 minus A, just 1 is Q plus Q squared plus Q cubed. And so it's infinite, and the homology is going to be infinite. And so I keep talking about the homology. So this is, it's, the homology is, in the most naive terms, a triply graded vector space whose gradings I'll call F, corresponding to some link L, whose gradings I'll call F, D, and K, such that this expanded Humphrey is A over Q to some power times, what's the best way to say this, sum over the degrees minus 1 to the F, that's going to be a homological degree, A to Q to the D, A to the K. In other words, the Humphrey is the graded Euler character of this giant vector space. At least that's what one would like. So this was proposed to exist in that work of Gukov, Schwarz, and Baffa that I mentioned. And then theory, and then it was defined shortly thereafter, or one definition of such a homology theory was given by Kovanov and Rozansky a little bit. The reason that there is still ongoing work on this is that one would like interesting geometric constructions for this homology that ideally make the topology of the link somehow manifest and make topological invariance manifest. And that's one motivation for looking for nicer and nicer constructions. Maybe a statement to make that, just a global statement. Chern-Simons theory conceptually was a really amazing development because it gave a way to define, at least physically, knot invariance, quantum knot invariance, the Jones polynomial, in a fully topological way that sort of made the topology of the knot in three-dimensional space manifest. It did not use Skane relations or combinatorics coming from quantum groups or things like that. And then other approaches to defining the Jones polynomial become computations. In Morley become computations in Chern-Simons theory. One would like the same thing for knot homology. There's been a lot of interplay with physics over the last few decades trying to achieve that. Okay. So, right. How conceptually would one produce a vector space invariant of a link in 3D TQFT? I leave you with that question while I watch the board. So, yes. So one approach is to go through braids and braid closures. Suppose a knot is realized as the closure of an n-strand braid, or link. Braid closure. An n-strand braid can be encoded in a function that I'll call lambda at the top, from an interval to the configuration space of n distinct points on C. It's C to the n minus the diagonals. And on the same page, the picture I have in mind, that if the interval coordinate is theta, which is soon going to become periodic, at a given value of theta, the strands of the braid are given by what's effectively this vector lambda. just an explicit presentation of a braid, to be able to close the braid one can further require, and we will require, that lambda of 2 pi is lambda of 0 up to some permutation. So suppose we're given this sort of presentation of a braid, then this is the thought experiment part of the thought. Suppose we also have a 3D TQFT with a family of boundary conditions. Lambda parameterized by points in configuration space. What should you say? Mod file. Then, well, we can put this TQFT in. So, and I, yeah, this is going to be sketchy, but this leads to concrete, actual concrete calculations. So then we can put the TQFT, or evaluate it, in a solid cylinder, or on. With at each angle theta on the boundary of the cylinder, the boundary condition be lambda of theta. So everything constant vertically, time direction, and on the boundary of this disk, it's not required to just have a single boundary condition. One can vary the boundary condition as we go around the angle, and will vary within this family. The space of states Z of this disk with lambda of theta boundary condition wrapping around, looking over. So first, this will be a vector space. Moreover, the dependence on lambda will turn this into a sheaf over the configuration space of all possible quasi-periodic functions. space of the configuration space of points on a plane on the sun. And okay, well, great. That is so far not super useful for defining a topological invariant of even braids. But if we are further in a situation such that the UFT depends in a locally constant way, or rather boundary conditions depend in a locally constant way on lambda. And so in a homological TQFT, what I have in mind is that variations of lambda would be exact. Then this is not just any sheaf, but rather takes the form of a constructible sheaf, or sheaf with locally a flat connection. And in fact, since I've removed the diagonals in the nicest situation, it's just a locally constant.
So when you write configuration in C, this already you're dividing already by the symmetric group, right? So
it depends how you define configuration space. Sure. In my head, I was using a definition in which they're labeled or ordered points. It would have been far more efficient to just not order them. Great, and so in particular,
where's
this vector space will be invariant under local deformations. Yes.
I didn't understand where the boundary condition is imposed. In this, I didn't understand in this picture where the boundary condition is imposed.
So, so it's imposed everywhere on the boundary of the solid cylinder, but it varies as we move around this outside circle, and it varies in a way that captures the information of the braid. The same setup is what's used in like all geometric constructions of Kavanagh for Humphrey homology. In Kavanagh, this is not a solid cylinder; it's an empty cylinder, and in Humphrey, one needs the bulk to be there.
Can I ask a question?
Yeah.
It seems that the natural map is not restriction, but the sheaf naturally has restriction maps. But it's the opposite way, because if you have a configuration that has boundary conditions in some open set, it also has boundary conditions in some bigger open set in configuration space. And not that it matters too much because it's locally constant, but I don't see how to restrict, right? If you have some open set and this.
Oh, you mean what? Sorry, how it turns into a sheaf?
Yeah.
I guess it's a vector space with a connection, and the thing you would ask for physically is what sort of connection is that?
Okay.
Is it a holomorphic connection or is it a flat connection? And these are your basic options.
I see.
UFT.
This is flat.
And this is So if you set it up properly, and if you actually want to get topological braid invariance, it had better be a flat connection.
Okay.
For Humphrey, this sort of rough picture gets one more ingredient. That I'll mention quickly because I'm going slowly. So we need a triply graded homology theory. In the Humphrey setups, the underlying TQFT will be of cohomological type, as in Justin's talks. So all categories and vector spaces will be DG objects. There's a differential everywhere. There's a notion of homological degree. So the F homological degree in Humphrey should match homological degree of fermion number. In the TQFT, Q degree ends up coming from some auxiliary non-homological grading. These disk state spaces, and A degree comes from something else that requires the bulk. A degree K corresponds to inserting a line operator. K, which in TQFT terms is an element in the category Z of S1 in the middle. And so the picture gets modified a little bit and looks like, I'll look the board up in a second. So there's some extra defect thrown into the middle here. Some boundary condition wrapped on the outside and some extra defect in the middle. And one can then, so needs to somehow compute a space of states. In that configuration. And Humphrey homology gets computed one A degree at a time. They don't interact with each other. Okay. So Oblomkov and Rozansky realized this sort of setup in a three-dimensional B model. The 3D theory is one of these n equals 4 theories that has been discussed now many times. It has group, it's a gauge theory with group GLN and representation adjoint plus fundamental. And this is kind of a famous theory and famous stack. So T star of the representation, I give it some coordinates. X, Y, n by n matrices, and a column vector I and a row vector J. And then the Higgs branch, the thing that's T star V symplectically, algebraically, symplectically reduced by G, looks like the zero locus of the complex moment map, which says xy minus ij is an n by n matrix is 0 mod GLN. And the stable part of this is the Hilbert scheme. This is This is a classic quiver construction of the Hilbert scheme of endpoints on C2. Special case of ADHM. In the B-twist, so this is all, it's going to be a B-twisted theory. The category of line operators, Z of S1, is just coherent sheaves on the Higgs branch. I claimed that there were elements in this Z of S1 category called line operators that count a degree, and the ones that are relevant here are kth antisymmetric powers of the tautological bundle on the Hilbert scheme. The boundary condition where all of the interesting information about the braid lives is complicated. You should listen to our talks of Lev for details on this boundary condition. It roughly involves coupling to a two-dimensional B model whose target is the flag manifold for GLN. The flag manifold for GLN as a Kähler space has cotangent of the flag. Cotangent flag is a resolution of the nilpotent cone and has n-1 resolution parameters.
Sorry, can I ask a stupid question? How do you relate this Z of S1 thing to Justin's description of the B-side line operator category, which was something like quasi-coherent sheaves on like maps from S1 Durand to...
I'll answer that later, but it all collapses. When you impose a stability condition, it collapses to something finite. There's a... the loops are locally trivial. In Justin's description, there's a loop space there, but the loops are trivialized in a derived way. So this starts out as a loopy thing, but it's you may also need a Betty version of the thing Justin described to actually get this on the nose. His has a few more objects in it.
I think when you impose the FI, they'll both be the same.
Right, so the boundary condition B lambda is roughly involves coupling to a 2D B model with target T star flag for GLN with complex Kähler classes. Depending on lambda. And now the statement, if you're coming from a math perspective, may not make any sense to you because the B model is something algebraic and doesn't know about Kähler classes, but that's precisely the point. One wants parameters here that in cohomology the theory doesn't actually depend on in order to get topological invariance at the end. I'm sorry, I'm not going to dwell on that because I want to say things about the A side.
Just say that these are the wall, like that the monodrome means these wall crossing functors that people.
Yeah. So yeah.
Variation.
But so one approach to computing things. that Leblanc and Wrożanski describe in their many papers, amounts in physical pictures to inverting this solid cylinder with a line in the middle, sort of inverting the boundary so that it goes inside out, and sort of like this. So the boundary now wraps the inside of something empty. The line is up there, and if we wrap the same boundary condition around in sort of an empty core and shrink it, this should define yet another element of Z of S1. It's another line-like object, should define another line operator. And that construction made precise leads to using the data of a braid to define a second sheaf on the Hilbert scheme. And L was an element of this category. And so this was a rather cool development, realizing that braids give you sheaves on the Hilbert scheme. And then Homology homology at a degree k comes from Hom, or from derived Hom, between these things. So sum over homological degree and q degree gets expressed as x between LK and this other sheaf. And q degree comes from the Hamiltonian C star action on the Hilbert scheme. Okay, that's the B side. Let me say things all too slowly about the A side. So this three-dimensional Hilbert scheme theory turns out to be self-mirror. So we want to apply 3D mirror symmetry to this entire construction to get something on the A side. And this is an extremely special theory whose Coulomb branch is the same as its Higgs branch. And so the 3D theory is, again, the one labeled by group GLN, and representation adjunct plus fundamental. The relevant moduli space now, one of the relevant moduli spaces, is the Coulomb branch. And so the Coulomb branch is now Hilbert and C2. They're both Hilbert schemes, but this is the one we're going to find sheaves on in the A twist. The category of line operators a priori looks nothing like sheaves on the Hilbert scheme. There's a beautiful paper of Ben Webster explaining how to get from what I'm about to write down to sheaves on the Hilbert scheme. But in the same terms that Justin introduced it, Z of S1 looks like D modules on the, well, in an algebraic setting, can be expressed as D modules on the algebraic loop space of the stack V mod G. So it's I'm sorry for going way too fast here. I'll focus on K degree, on A degree 0. The line operator corresponding to 0 A degree in physics would be called the trivial line or the identity line. It's the one that does nothing. And in this description of the line operator category, doing nothing means that loops can be contracted. So it's the structure sheaf of the arc space as a D module. The boundary condition has a remarkably intuitive description in the mirror. One doesn't need to couple to any fancy A model on the boundary. Roughly, for the boundary condition, we're going to require at the boundary that I is constant. Sort of a generic constant vector, and the eigenvalues of x, the GLN fields are lambda. This description of the mirror comes, for me, from a brain construction and applying S-duality in string theory. This is not a thing that I would know how to compute purely in field theory in some direct way. So claim this is roughly what the boundary condition should look like, and that leads to a guess for an algebraic construction of the space of states in this cylinder. The algebraic approach it goes as follows. It requires, try to finish with this, and maybe a brief statement about vortices. It requires some assumptions. So we're going to compute, algebraically, we're going to try to identify some object in the category of line operators, and compute the state space after this inversion as a hom in the category of line operators between some very simple thing, which is the structure sheaf of the arc space, and something that depends on the braid. So, yeah, claim. Let's suppose the braid is algebraic. Which means, for these purposes, that there exists an n by n matrix with polynomial entries such that its eigenvalues on a very, very small circle produce our desired profile lambda of theta. Then there's a very good guess for what the object in the category of line operators ought to be. that this, I'll call it E lambda again, but it's not a sheaf in the same sense that it was in the B-twist, is just the skyscraper sheaf at gamma 1. In other words, so gamma 1 is a point in GLN, in the loop space of GLN plus c to the n. And we can take a skyscraper D module at that point. And assuming this, the hum, derived hum in the category of D modules on the loop space has a geometric construction. So it's hum between k and 0 and the c lambda. So this takes the form of the Moore homology of the intersection of the supports of these two sheaves fibered over the loop space. And that sounds, if you have not seen this sounds quite horrible. But there's an algebraic moduli space here. And gamma, where and gamma is just the set of elements of the loop group such that acting with this element of the loop group on our braid matrix lands us in Taylor series rather than Laurent series. Lands us in the arc space. I will finish immediately. And this whole thing gets completed by the Taylor series group. This is an eminently computable thing. I would, since I'm out of time, I will leave it as an exercise, be able to do in 5 minutes, to compute the a degree 0 part of unknot homology from this. To do that, I need to tell you one last thing. What is Q degree here? Q degree is literally degree. So the space looks roughly like the affine Grassmannian. If we didn't have this extra condition, we would be looking at the loop space of GLN mod the arc space of GLN, which is the affine Grassmannian, which has components labeled by pi1 of the group. And so D, Q degree, corresponds it labels components of this M gamma. And I won't just leave it there. So Oscar and Nick Garner, when they were students at Davis, looked at this thing and proved a nice theorem that this gamma space is the Hilbert scheme of points on a plane curve singularity, which connects this construction, this proposed construction of knot homology, with the work of Blomkamp, Rasmussen, and Schende, who conjectured that Humphrey homology should come, of algebraic links, should come from Hilbert schemes of points on plane curve singularities.
We're a bit short on time, so.
Yep. So I won't write down the theorem, but this isn't just like part of this was physics guessing, and at the end of the day, one gets something very concrete. So I don't have time to write it down, but what one would hope is that there's an analytic version of all of this that computes the same space, also generalized to non-algebraic links, using a version of vortex equations on a disk with an appropriate boundary condition at the boundary of the disk. And if anyone is interested in that, I'm happy to supply details, but most of them come from putting together other talks from this workshop. And in particular, Andrea's and Justin's. So Andrea talked about state spaces in the A model without boundary, but here we have a boundary and a boundary condition. And
what kind of boundary condition?
Hmm?
What kind of boundary condition is this?
It says that it's a non-analytic boundary condition. That looks like that for x and y. So it's vortex equations in the sense that have appeared in this conference on a disk with this weird boundary condition that doesn't just involve x alone or I alone, but involves complex conjugates. This is a Lagrangian and an appropriate complex structure. And the claim is that some homology theory of this moduli space ought to be computing, not homology for arbitrary lengths. And I would love to make that more precise. Sorry, thank you.
Listening tutor. We have time for one question. We can also ask him later.
You're at lunch.
I actually have a question. So there's this space M sub gamma seems like it's also stratified by things that where this lands in Taylor series versus, and then things that land in like Z times Taylor series.
Absolutely. That's where higher A degree comes from.
Okay. So it corresponds to taking different
powers. So if we land, so we can change the thing that we land in.
Yeah.
In fact, by imposing a partial parabolic structure here, and that will give us higher A degrees. Yeah, there are options.
Well, let's think to it again.